Welcome to my ECE202 final project presentation, the central server-based smart camera system. Let's first start with some background. With the fast development of machine learning model compression and the edge device AI framework, it is practical to deploy machine learning programs to edge devices. More and more electronic devices are able to become a smart device. One of the most important areas is smart cameras. Smart cameras can be widely used in personal home security, warehouse security, or factory assembly line monitoring. Currently, most of the smart cameras in the market using onboard chips for AI computation. Although those smart cameras have fast AI connection and are able to connect to smartphones or computers, their entire computation is limited by their onboard microcontroller. Such design leads to several potential problems. First, most of those cameras can only run simple person detection neural network due to the limited computational power and RAM. Most of the high-performance neural network requires hundreds of megabytes to store and fast GPUs to inference a model, which is unlikely to be available on a smart camera due to the cost and physical size of those cameras. Second, it is impractical to update such camera because most of the time the camera module is good enough for many years, but new machine learning algorithm updates fast and would require more computational power in general. Update such camera for new AI performance would require replace the entire camera module. However, those indeed have large commercial security systems, but they are usually solely rely on their central computation server and cost around $6,000, which is not very practical for common users. But is it possible to have a system that takes advantage of both design with reasonable price for various use case, which leads to the goal of this project?
The goal of this project includes designing a central service-based camera system.
Maximize the use of the edge device AI computation resource. Run simple person detection on edge device. Run advanced person detection on central server. The dynamic priority system integrate edge AI and the central server for maximum efficiency. The challenge of this project including design pipeline for central server-based smart camera system, a task scheduler inside the embedded system. The hardware including a Raspberry Pi Pico, the ArduCam, and the central server, which can be a MacBook or Raspberry Pi. So the Raspberry Pi Pico has a ARM Cortex M0 chip, and it has 256 kilobyte of RAM. It costs $8 on Amazon, but it's actually $4 before the silicon shortage. I implement a simple motion detection algorithm using C++. And the TensorFlow Lite is used for person detection, and it costs 130 kilobyte of RAM itself. And using FreeRTOS to schedule all those tasks inside the Pico. And the central server using PyQt for the user interface and runs the neural network YOLO version 3. The toolchain for this project including ARM GNU compiler, C and C++ as a programming language. The software build system is CMake, and the code editor I chose is VS Code. The debugger server is the OpenOCD debugger server integrated in the VS Code. The debugging probe right here is another Pico board. So you can see that the image on the right has two Pico boards. One Pico is used for neural network and motion detection. Another Pico is actually served as a programmer and a debugger. So the Pico team, they actually provide the software to turn their Pico into a programmer and debugger. The overview of the approach. The graph shows the hardware and the working pipeline for the system. The ArduCam and Raspberry Pi Pico can be treated as a smarter camera system with limited built-in AI capability, and the Raspberry Pi or the computer served as the central server in this project. The ArduCam will capture the image in YUA422 format and transfer it to Pico through the SPI interface. The Pico will perform motion detection, and if it detects a motion, then the person detection using TF Lite will be triggered. All those tasks are scheduled using the real-time operating system called FreeRTOS. The detail of the implementation will be mentioned in the next section. Although I only have one camera module available for this project, the system is actually optimized for multi-camera system. Inspired by the FreeRTOS task priority system, I designed a dynamic priority system. The system will continuously update each camera's priority based on the computational result inside the Pico and the result from the central server. The camera with higher priority will have their data processed faster in their central server. The implementation detail will be mentioned later in the priority system section. System is to first capture the image and transfer it to a central server. After the image is transferred, the Pico will perform motion detection. The implementation of the motion detection is simple yet efficient. A frame difference is computed after every new image captured. This is simple done by applying pixel-wise subtraction between current frame and previous frame. Then instead of applying complex operating such as contour find, I simply find the number of the pixel with values above certain preset threshold. If the number of those pixels are greater than 2% of the total pixels in the image, then consider that there is a motion between two frames. The reason for such simple design is because the motion detect will take place after every image capture, so it needs to be fast. In fact, the entire motion detection only takes about 2 milliseconds in the Pico. After the motion detection, if there is no motion detector, then the camera will just capture next frame. If there is motion, then perform person detection using the TF Lite. The TF Lite model is a mobile Lite version 1 and is quantized to int A. The model can be directly downloaded from the TF Lite example repository. Here is a demo of the frame difference motion detection.
Despite the logic of the task is very clear, the system is not practical.
So it simply builds the pipeline with the bare metal programming. The table here includes the each task execution time. As we can see, the execution time of the person detection neural network takes about 0.8 seconds. With all other tasks, if there's motion, then the image will update at 1.1 seconds per frame. This is obviously not acceptable in a smart camera system. Worth to notice that because I'm using the serial port to transfer the image from Pico to the central server, the image transfer takes about 200 milliseconds. In the real application case, the bandwidth between the central server and the smart camera is much higher, so the transfer time should be limited. Um, Most of the smart camera now support 1080p at 30 or 60 fps through Wi-Fi. However, most of the microcontroller does not have much improvement in the neural network inference speed. So the bare metal programming like this will be large slowly down the refresh rate of the smart camera. The solution for this problem is to using RTOS. The RTOS I'm using in this project is FreeRTOS. It will suspend the task with lower priority and execute the high priority task first. Then, if the time allows, it will continue to execute the lower priority task. In the Pico, the capture image and the transfer to the central server has highest priority. Because the motion detection only takes about 2 milliseconds, I make it first priority too. I set those tasks to execute every 300 milliseconds so that the lower priority person detection task can have time to execute. On the right, the graph showing the schedule of the task. You can see that the person detection is suspended because the program had to make resource for the capture and transfer, as well as motion detect. Look at the central server. In this project, the camera server's job is to run a more advanced person detection neural network. Here, I'm choosing YOLO version 3. Other tasks of the camera servers are to receive data from the camera and adjust the camera's priority accordingly. The detailed implementation will be explained later in the priority system. The central server does provide a GUI written in PyQt, and the neural network is implemented using PyTorch and using a pre-trained model. On the right is a screenshot of the GUI of the central server. You can see that the image is displayed in the center, and the person detect is bounded by the green box, which is detected using the neural network.
Imagine that a smart camera are used in the warehouse. There are more than 20 of those cameras that keep sending image to the central server, and the server needs to process them in real time. In this project, one of the central server I use is my MacBook Pro with Internet's i5 chip. I'm running YOLO version 3 on PyTorch with no resolution 128, and it took 0.3 seconds to process the image. It will take 6 seconds to process one frame from those 20 cameras. Of course, in real application, we can use GPU and process multiple images in a batch. But my point is that the central server could have large pressure when running complex neural network or when multiple cameras connect to it. Multiple camera systems are very common nowadays, even in home security system. If there are multiple cameras connected to the central server to satisfy all the computation needs, one choice is to make the central server power enough to handle all cameras' needs. However, such design leads to better hardware in central server and higher costs for cloud server. To address this problem, I developed a dynamic priority system. The priority system is inspired from FreeRTOS's priority task scheduler. The central server will first process images for the cameras with high priority. Below, I introduce how the camera's priority is classified and decided. The camera has three priorities. The default, and the lowest priority is 1. All cameras start with priority 1. If the pico detects a motion, then the camera's priority changes to 2. If the pico detects a person, then the camera's priority will increase to 3. Each time Pico changes the priority of the camera, it will transmit this information to the host server, so the host server is aware of the priority of the camera. Due to the relatively low accuracy of the Pico system, the Pico can only increase the camera's priority, not decrease. The central server will process a camera with higher priority. If the host detects a person in the camera's image, then the camera's priority increases to 3, if not already. If there's no person detector, then the camera's priority decreases to 1. So the host server can both increase and decrease the priority of the camera. Also, to prevent that one camera is not being processed by the central server for a long time due to other camera's high priority. If a camera has not been processed for more than 3 seconds, then the camera's priority will increase by 1.
In multiple ways with different baseline, including video refresh rate, person detection accuracy. The way I test the camera system is to play a surveillance video in front of the camera and using the central server to record the test data. The surveillance videos are from the VRACT dataset, which is a video dataset of a surveillance domain. First, I evaluate the video refresh rate on the central server. The baseline implementation is smart camera system with a bare metal implementation and compare with the RTOS implementation. Below graph shows the FPS of those two implementations and the test on 8 minutes video. From the plot, we can see that when there is no motion detector, no person detection is executed. The FPS of the bare metal implementation has 4 FPS, which is the highest possible FPS using the AltraCam UVF422 format. However, when there's motion in the graph, the FPS drop to below 1, which is not practical in the real-world application. The high FPS is useless when there's no motion in the video, because the server will just receive repeated images. The RTOS implementation has 3 FPS in most of the time, with or without motion detection. This advantage will be further enhanced when the image transmit overhead is smaller, because the difference between the neural network overhead will be much larger than the image transmit overhead.
Second,
I test person detect accuracy on the camera system with and without central server. During the experiment, I noticed that the accuracy of the person detection on Pico has significantly decreased when the person inside the image is far away. I think this is due to the low capacity of the 120 kilobyte model. Also, when the relatively simple structure of the model, the accuracy decreased a lot when there are multiple people inside the scenes. So in order to make this a fair test, instead of using the entire video, I crop a square area from the video so that the person looks larger when the camera captures the image. I tested on a 16 minutes video, record both the person detection and the result from the Pico board and the result from the central server. I compare them with the ground truth and the result shown in the table below.
This is a short demo of showing how system work and is checking during the video evaluation. The video is accelerated for interest of time. For more information, please check the report. Thanks.